What's up, ladies and gentlemen? This is your host, Clay Swackhammer, coming back at you with another exhilarating episode of Annotated MATLAB Codes. Today we're going to be doing some image analysis. So if you remember, if you watched the previous video, we just did some image processing. Now let's look at this overall summary to get an idea of where in the workflow we are. So in this video, we're going to assume that we already took some images, and then we already did the image processing, which is getting the particle sizes out of those images. Next, we want to get some information that's easier to interpret than a list of 300 particle areas. Doesn't look so good on a poster. So what we're going to do is some Rosen-Ramler fitting and then come up with a Rosen-Ramler value of x50, which is basically a median particle area on an area basis. We'll also come up with a numerical or model-free x50, and I can explain the difference between those two. So the first thing that we're going to do is download this file, ImageRR analysis. So let's download. Where is that? Download. Now we'll put that on the desktop. And next, we're going to download test areas. Now this is a CSV. It's basically something, it's like an Excel workbook. This is a little better than Excel for this purpose, actually, because it's a better archival data format, comma-separated values. So we'll take a look at that to start off. Now, really what this has are just two giant lists of particle areas. We might have a lot more. If we had run 10 images on the image processing step, then we'd have 10 columns, and each one has two rows in the header, which is the image file name, and then just this thing that says particle areas, millimeters squared, so this label. And for this first image, it had 40 particles, which were enumerated, and this one had, well, several hundred. So I think that the best way to do this would be include everything in a certain time point here. So maybe this would be areas 30 minutes or areas 90 minutes. And it would have all the areas for particles that were on images we took at that time point. And that'll make this an easy analysis. So next we're just going to open this MATLAB script, and please ignore the fancy color. It's just purely fancy. There's nothing different about this from the MATLAB that anybody else runs, other than the color scheme. Okay, so I'd like to keep this section get user inputs as the place to go when you just want to use this. You don't necessarily care to modify everything. And up here we have some idea about what this is going to do for us. What information are we going to get out? So we need to give it a file name, and this file has to be in the same folder. I think for now they're both on the desktop. So oops, back up. But the file name is just test areas, and we're going to put that in right here. And then plot. We're going to set that to true. That'll give us Rosen-Ramler plot. So the way this script works is it's going to assume that everything that we give it in this document is all going to be analyzed together. So it's going to take all these particles and all these particles and just combine them into one list, and if it had more here and more here, it would just append them as well. So that's why I think it would be beneficial to have, or really necessary, honestly, as it's set up right now, to have all of these column vectors be for images from the same treatment, whether that's a time point or what have you. Okay, so let's just see if we can run this. All right, keep going. You know why MATLAB takes longer the first time you always run a script than subsequent runs? Well, I'll tell you, because you guys can't answer it right now. The reason is it's actually compiling that code to a more basic code format. I'm not exactly sure what that is, but something other than this very high level kind of contrived MATLAB code that's very easy to read and has a lot of recognizable words. Well, it's compiling it into something that's easier for your machine to read And the result is the first time it builds that more basic code, so it takes longer to run. It also puts functions on kind of a short list, things like string cat or whatever. Okay, so that's a little bit of MATLAB for you. So this is going to give us the Rosenrandler fit. The blue dots are all the particles that were in these two columns, and the model, which is the Rosenrandler model. It's going to give us the R squared of the fit, the X50 value of B, and these in parentheses are the 95% confidence intervals for those parameters, and it's 452. That's how many particles did we fit, and then it'll show Rosenrandler X50 with a red diamond and the numerical X50 with a blue star. So I promised to tell you the difference between those two and also when it matters. So I guess I better do that. Now, the numerical value of X50 is nothing but the value of particle size at which we cross 50% of cumulative area. So we don't need to have any model whatsoever to find that. That's why I call it numerical or model free. We just line up all the particles from smallest to biggest, then express each one as a percent of the total, a cumulative percent of the total, and whichever one that crosses over to 51% or anything above 50%, we'll call that size X50. So this kind of thing breaks down a little bit when we have very few particles. For instance, if we only had one particle here and then one particle here, X50 would be like way up here, basically. This can be the case when maybe we have a whole bunch of really small particles and then we have two or three enormous ones. So this is a useful thing, but has some limitations, such as when we have very few particles, what we're calling X50 might be quite actually different from 50%. It could be up here at 70% if we had one particle here at 20 and then one up here at 70 and one more up at 100, our value of X50 on a numerical or model-free basis would actually be an area that corresponded to maybe 70% of the distribution. Okay, so that's sort of the limitation of the model-free one. Better give you the advantage of the model-free one. That can be in the case that the Rosenrandler fit is not good. It's just not describing this particle distribution very well. And that is always going to be the case when we have a bimodal distribution or any more than one mode. Then we might have to use X50 if the Rosenrandler fit just isn't cutting it. So that's the lowdown on that guy. Now the Rosenrandler X50 is nothing more than the size at which we cross over 50% cumulative area percentage, but for the Rosenrandler function. So the Rosenrandler function is given by this statement right here. It's just very similar to Weibull distribution or Weibull fit. So we're actually going to come up with values for the parameters here, X50 and B. We're going to do that by nonlinear least squares curve fitting, and then that's going to give us an actual mathematical equation for this red line. So if we basically solve that equation for where y equals 0.5, maybe it's y equals 50, it depends on how you set it up, then the corresponding x value will give us the Rosenrandler X50. Okay, so that's what it is. The advantage of the Rosenrandler X50 is that it's always going to be at actually 50%. Even if we are only modeling 3 particles or something, this guy will always cross over at 50. The disadvantage of the Rosenrandler X50, well, there's really 2 of them. One is if the Rosenrandler fit is not doing a very good job, doesn't really help us very much. It's just describing a distribution that's not really the one we're working with. For 2, in the case that we have a very sparse data set with, like I said, maybe only 5 particles or something, it's possible that we don't have any particles anywhere near this value. This is just giving us a statement of where we think it would be, if that makes sense. I think the bottom line or takeaway from that is if the Rosenrandler fit is well describing the distribution, then we probably want to use Rosenrandler X50, and if it's not, we probably want to use numerical x50. For now, I give you both of them. If you want to modify anything on this plot, you can easily do that. It's all down here. If plot, and basically that means if plots is set to true, we're going to display the plots. If plots is set to false, then we do not display the plots. So we're also going to get some data here in a variable called out. And this is something you could easily copy paste into Excel or whatnot. So it's going to give us a file name, the number of images in that file, and this file being this CSV. Okay, the numerical x50, the number of particles in the data set, particles per image, now it's just this divided by the number of images, Rosen-Ramler x50 and its confidence interval, and then Rosen-Ramler spread parameter b and its confidence interval, and finally the r squared. So you could easily take this, copy the whole thing, do something like that, put it into Excel. Let's see. Great. Now you could copy another row here and here, so on and so forth, put this into your master data set for your experiment. Now remember that by the time we're doing this kind of analysis, we've already taken the images and we've already processed the images. This is really just the last step. All right, I hope that clears everything up for image analysis. This was your host, Clay Swackhammer, signing off of another episode of Annotated MATLAB Codes.